say anything? No. I don't have anything to say. I can't think of anything. Okay, then let's get started. Welcome to 15.2, our next trig lesson. All right, define and evaluate the basic trigonometric functions. Hopefully some of this maybe is review. If not, you'll be fine. So we're going to be using the unit circle again. So let's spark our learning. So looks like here we've got Jonah's car on a Ferris wheel. And so we've got an angle here. And the height of Jonah's car changes as the angle makes with the horizon axis changes. So his height above the ground, if you whatever, is changing as he goes around as this angle changes. So what mathematical questions can we ask? So how fast is his height changing, or how is it changing? In order to do that, we would probably need to do some trigonometric functions to make that work. So we could essentially make a function that figures out his height from the ground here based on this theta. We're not going to do that right now because we need to learn how to do it first, right? Let's go. Define and evaluate the basic trigonometric functions. So I'm hoping that this is going to be a little bit of a review, because theoretically you should have gone through some of these functions before, but just in case, we'll figure it out together. So we can use these special right triangles in a unit circle. And when we get to that unit circle, I'll show you that it all kind of works out really well for the right triangle. Remember, a right triangle is any triangle that has a 90 degree, and then you have these two other angles. And remember, we have these trig functions that go along with a right triangle. So if we have our right triangle here, and let's say we have our angle theta right there, we have our opposite, we have our adjacent side, and we have the hypotenuse. So that's what all these are talking about. So we've got our sine, so that's going to be our opposite over hypotenuse. We've got our cosine, adjacent over hypotenuse. Then we have, the only thing we have left is our tangent, which is opposite over adjacent. So all of those still hold. And if you don't have those memorized already, that's going to be a good thing for you to commit to memory. That's something that I'll probably easily remind you of, but for your benefit, you need to remember these trig functions. So as hopefully you've seen before, there are two special right triangles that we just are very, very useful to have. So a 45-degree triangle or a 30-60 triangle. So again, we've got pictures of them right here. So for a 45-45, couple things you can see. I mean, obviously, your two side lengths are going to be the same, so they're going to be A. And then your hypotenuse is A times the square root of 2. So again, that's going to be something that you will want to remember. And then our 30-60-90 triangle. So the way I always remember this is, so I always remember that 2 is definitely the longest hypotenuse. I can always remember that. But then I always remember 1, 2, square root of 3. Like 1, 2, 3. I think a lot of people might even call them 1, 2, 3 triangles. But That's just how I remember it. Again, these are things that are going to come up over and over and over again, so it's good for you to have in memory as opposed to always having to look at a piece of paper, things like that. So you can start to imagine that when we're in our unit circle, this hypotenuse right here is going to equal 1, right? Same thing here. This hypotenuse is going to have a length of 1. And so now things get to be a lot easier to figure out. So actually, I think I misspoke. If we're using our radius, we can define our radius right here as 1. That way, the math gets easier. So the A, in this case, the A is 1, especially right here. Anyway, we'll see once we get into the unit circle. Let's get there. So you can describe the triangle in the unit circle. You can use these triangles to find the value of trigonometric functions for the angles 30, 45, and 60 degrees. So let's check this out. So we've got our 45-degree angle here. This is our unit circle. Remember, the radius of our unit circle is 1. So I was kind of right with that one. I think I just confused myself, but that's okay. So if we know our radius is 1, then we can find this point right there, which is going to be the square root of 2 over 2, square root of 2 over 2. And the way we found that is we just used these equations. So we had, 1 equaled a square root of 2. So then we divided both sides by square root of 2. So then we had 1 over square root of 2 equals a. We don't like rationals on the denominator, so we multiplied by a very special version of 1 called square root of 2 over square root of 2. So then we had square root of 2 over 2 equals a. So then from that, we can figure out the x and the y coordinate with this one. So that's how the math looks. I'm not going to do the math for each one. That's kind of some easy algebra that you can do if you so desire. But we find these points at the unit circle using the 45, 30, 60 degree marks as what we know. So then let's see what questions they've got. In each of the triangles, how does the hypotenuse of the triangle relate to the radius of the circle? In each one of these triangles, the hypotenuse is 1. So the length of the hypotenuse is equal to the radius of the circle. Yay! How can you use the relationship between the sides of a 45, 45, 90 triangle or a 30, 60, 90 triangle to determine the coordinates of the points where the hypotenuse of each triangle intersects the unit circle as previously shown? For this triangle with its shorter leg along the x-axis and the y-coordinates are reversed of those for the 30, 60, 90 triangle with its longer leg on the axis. So that's true. So that's just saying, so if we have square root of 3 over 2, 1 over 2 here, they're going to be reversed if you switch that triangle around. Okay. For a 30, 60, 90 triangle, the leg lengths of 1 and square root of 3 represent the x and y coordinate. So I would argue a little bit with that because that 1 is the hypotenuse. That was the trap that I almost fell into earlier. So this is not 1. This is something that we have to algebra to figure out, which they kind of did for us with that point right there. So now for a 45, 45, 90 triangle, the x and y coordinates are the same and are equal to square root of 2 over 2. Hey, look, square root of 2 over 2, and they're the same. For both types of special triangle, the horizontal leg extends from one end of the hypotenuse at the origin along the x-axis to a point directly below the intersection point. So the intersection point has the same x-coordinate as the length of the leg. The vertical leg connects the x-axis to the intersection. Yeah. So that's a really confusing way of saying in all of these triangles, you've got one leg that's along the x-axis that would then correspond to the x-coordinate. Then you have one leg that is on the y-axis, or that connects it, that would then correspond to the y-coordinate. So use the triangles to find the values of the trigonometric functions for the angle of rotation theta. So I'm bad at this, so you know what I'm going to do? I'm going to draw a picture. So we'll change some colors. So here is my coordinate plane. We'll start with 30. So that's 30. That's 60. So we got 1. So my relationship is 1, 2, square root of 3. But my x-coordinate is going, so for this dot right there, let's do some math. Actually, we don't have to, it's up here. Right there. So my coordinate, let's erase that, is going to be square root of 3 over 2 and 1/2. So, let's see here. Oh, hang on. I need those lengths, right? So this is going to be 1. Oops. That's going to be 1. And our relationship is up here. So this is going to be square root of 3 over 2. And this is going to be 1/2. So I got those from these two coordinates right there, in case you're wondering. So let's see here. Sine of theta, opposite over hypotenuse. So that's just going to be 1/2. Cosine is adjacent, square root of 3 over 2 over 1. Square root of 3, there you are. Couldn't find it. Oh, let me guess. It's not going to let me drop it in the right spot. Oh, it does. Okay. So then tangent is opposite over adjacent. So what that's going to end up turning out to be is going to be 1/2 over square root of 3 over 2, which is also equal to, you can, anytime you have something in the denominator, you can multiply the top by its reciprocal. So that's going to be like 1/2 times 2 over square root of 3, boom, boom, 1 over square root of 3. So I'm showing it now. Typically, that's something you would either just know or whatever. So I'm picking this one because they rationalize the function. Remember, you don't like a radical underneath there. So then for 45, I'm going to go into the 61 since I kind of already have that one laid out. Well, no. I need to rework that all. So for the 45, again, let's draw our picture. I'm just going to come up here and kind of sort of steal their picture. So our hypotenuse is 1, and both of our values are going to be square root of 2 over 2, square root of 2 over 2. So the sign is going to be the opposite over adjacent, so that's square root of 2 over 2. Cosine is going to be the same, and tangent is going to be this over that. They're the same number, so they will cancel out. And then our 60-degree angle, let's go up and look at that one. So here's our little picture. So our x value is going to be 1/2. Our y is square root of 3 over 2, and that is 1. So our sine is going to be our opposite over adjacent, so square root of 3 over 2. Our cosine is going to be 1/2 over 1. And our tangent is going to be the opposite over adjacent. Our 2's here are going to cancel out. So that's just going to be square root of 3. Yay. So these are things you should get very familiar with. I need to get more familiar with them too. So how do the values of the trigonometric functions relate to the coordinates of the points of the intersection of the hypotenuse of the unit circle? So the values of the blank function are equal to the x-coordinate. So the values of the, let's see here, which one? Cosine, right? So what I'm doing right now is I'm imagining an angle right here. So I know that one's always 1 because it's a unit circle. So the cosine is going to give me my x value. And the sine, which is going to give me this part, is going to give me the y-coordinate. What? Cosine. Do they want me to spell it out? Oh, yeah, they do. Whatever. There. Does that make you happier? Oh, I still can't spell cosine. Leave it to me to not be able to spell cosine. Well, okay. It's fine. Can't spell. Define each coordinate x and y of a point, x and y, on the unit circle in terms of a trigonometric function of the angle rotation theta. So it's basically rewording what we just kind of talked about up here. So the values of x equals cosine of theta, y equals sine of theta. So we can use these later on a lot. All right, here's where we get to figure out whether you were paying attention in geometry/trigonometry if you've had it before or not. So we're going to explore basic trigonometric functions again in our unit circle. Now, one thing I would like to note, because I'm sure nobody has forgotten it, what quadrant of the unit circle are we in, or of the coordinate plane are we in? That is quadrant 1. So notice how this goes backwards from how you read. So it goes 1, 2, 3, 4. So it goes counterclockwise. So 1 starts in this corner, 2, 3, 4. Again, these are called quadrants. So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4, as a quick reminder. So you can have this 45-degree angle in each one of these quadrants. And so you can use this relationship to figure it out. Doesn't matter which quadrant you're in, but it might add or take away a negative sign. So let's see what they are asking here. In the first quadrant, with one leg along the x-axis, the triangle is then reflected into each of the other 3 quadrants as shown. What are the coordinates of each of the points labeled A, B, and C? A, B, and C. So this one, so again, this is your x, and this is your y. Now remember, this is just your normal coordinate plane. Okay, so if you go left to the origin, what numbers are you in? You're in negatives on the x-axis, but we still went up. So this one over here, A, is going to have a negative x value and a positive y value. Okay, so let's do that same thing down here. This time, we went down and we went to the left. So that's going to be negative and negative. So this one in C, in the fourth quadrant, we went to the right, which is positive along the x-axis. But we went down, which is a negative y-axis. Remember, don't get freaked out by these fractions. They're still just numbers. They're just numbers. So they can be positive, negative, and they can still correspond to lengths. So let's see, we can't find, let's go ahead and label these. A, B, C, D, E, F, G. You know they changed that alphabet on me, right? Anyway, A is negative, positive. B is negative, negative. C is positive, negative. Oh, it's the top one. Whew, that's awesome. I don't have to check the rest of them. How could these coordinates be used to find sine, cosine, and tangent of the reflected angles in the quadrants 2, 3? So using these coordinates, you can figure out the lengths of all of those, whatever. And also, because of that relationship we just talked about right before in the previous screen, because cosine of theta is equal to x, and sine theta is equal to y. They're missing a space here. On the unit circle, you can use those to figure out all of the sine, cosine, and all that good stuff. So what is the value of the angle of rotation theta in a counterclockwise direction with the terminal side that passes through point A? So it wants to figure out what this angle is here. And this is where we get to start thinking a little bit, right? Ooh, thinking. So we'll think with my green. So this angle right here is what? Oh, shoot. Is 180 degrees. But our blue angle is how many degrees up from 180? You're right. It is 45 degrees. So we can say 180 minus 45 is going to equal 135. So our blue angle is 135 degrees. And explain how you know. I worked through the process with you, so you're good to go. So now find the values of theta for the angles of rotation in a counterclockwise direction with the terminal side passing through point B and passing through point C. So we can do the same thing. So we've got 180 plus 45 degrees. Oh no. 180 plus 45. I totally know that off the top of my head. I'm not bad at basic arithmetic. So that's B degrees. And then this one is, you could either add a bunch of stuff, or you could just do 360 minus 45, right? 360 minus 45, 315. So for B, it's 225. For C, it is 315. Yay! So then for a 30, 60, 90 triangle inscribed in a unit circle so that theta is equal to 30, reflect the triangle into each of the other three coordinates. What are the coordinates of the points in the intersection of the hypotenuse and the unit circle? So I'm going to do a little multiple choice stuff here. So we see that all the numbers are the same, just the negative sign is moving, right? So, and this is a pattern that you should maybe pick up on. What are all of your thetas, or your sine and cosine, going to be in quadrant 1? They will both be positive, right? Positive, positive. What about quadrant 2? Oh, shoot, that looks terrible. What about quadrant 2? So x is going to be negative, y is going to be positive. And quadrant 3, x is negative, y is negative. And quadrant 4, x is positive, y is negative. So let's see, quadrant 2, I'm looking for a negative positive number. Quadrant 3, I'm looking for a negative negative number. Set of coordinates. Is that something maybe you should remember? Yes. Use these coordinates to find the sine, cosine, and tangent of all the reflected angles in the quadrants 2, 3, and 4. So I'm going to steal their angles up here. So our x coordinate is equal to our sine theta, so that's going to be square root of 3 over 2. Our cosine is going to be negative 1/2. And then our tangent is x divided by y, right? Because that will get us opposite over adjacent. So in this case, that's going to be a negative square root of 3. Maybe, maybe not. Okay, I'll do it. So opposite, so that's going to be square root of 3 over 2 times the reciprocal. I'm still sticking with negative square root of 3. That's what I'm finding here. Did I do it wrong? Okay, fine. I'll look at it. So the tangent is going to be the opposite over adjacent. Am I missing something? Okay, let's draw it out. Maybe I'm missing something. And I'm going to look foolish later on. So in quadrant 2, so it's like this. Our theta is right there. Sometimes also denoted as just that little curvy thing. And so for quadrant 2, my x-coordinate is negative square root of 3 over 2. My y-coordinate is 1 over 2. I was doing it wrong. So our tangent would be opposite over adjacent. So it is going to be, come on pencil, 1/2 divided by negative square root of 3 over 2. So then we get rid of this stuff. This is why drawing a picture is awesome. Always draw a picture. Times the reciprocal, negative 2 over square root of 3. So it's going to be negative square root of 3 over 3. So I did a couple steps there. If you didn't catch those steps, let me know, and I can go over with them again. Okay, so then we're in quadrant 3. That's going to be going down this way. Luckily, our x-coordinate is still the same. And our y-coordinate will be the same, just negative. So let's see here. Okay, negative 1/2, negative 3 over 2. And then tangent would be negative? No, that was a trick question, because think about it. In this case, you're going to have negative divided by another negative. So it's going to be the same number, just positive now. And then quadrant 4. So again, our x is going to be, losing my focus a little bit here. Our x is still going to be square root of 3 over 3. Our y is still going to be negative 1/2. And so then we can figure everything out from there. So our sine is negative 1/2. Our cosine is positive square root of 3 over 3. And then our tangent is going to be the same as this one. Did I get them all right? Nope. So let's look at my picture again. My sine is going to be 1/2. And then my sine for quadrant 3, which is down here, is going to be negative 1/2. Try to put the right one there. So then my cosine for quadrant 2 and 3 should be negative. And that's going to be negative 3 over 2, negative 3 over 2, and then this last one would be positive 3 over 2, and then tangent over here would be, oops, yeah, I don't know what I did wrong the first time, but all of that made sense. So, I don't know. Again, draw a picture. It is super helpful. So repeat part C for a 30, 60, 90 triangle inscribed in a unit circle where theta equals 60. So I'm not going to use your time here at home doing that. That's definitely something that we will end up doing over and over and over again throughout all of our homework. So get comfortable with the positives and negatives of the different quadrants. So identify the counterclockwise angles of rotation that result in the terminal side of the angle passing through the points identified. So this is talking about, I think they're referring to our picture up here and how many times. So every time you go like right here, this is 45 degree up. Every time you go 360, it's the same thing. And then your sine and cosines will be the same thing like every 360 degrees. Hey, look, here's that pattern. If you want to memorize it, go for it. But I would just remember your coordinate plane and think about, so it's positive over here, positive up here, negative over here, negative down there. So that's the way I remember it, but however you want to remember it works. And so that's just kind of everything that we've already talked about. So evaluate trigonometric functions given a point. So this is the same concept, but in this case, they are giving us a coordinate, x and y, and they want us to be able to evaluate our trig functions for this theta down here, given that we are no longer on the unit circle because we have an x and y coordinate. So it's, I don't know, it sounds worse than it is in my opinion, but let's just try it out. So don't forget, again, this kind of thing is just the same-ish that we've kind of been talking about if you think about it. So sine is still opposite over hypotenuse, but in this case, our opposite is this value, our y value, and our hypotenuse is right here. Or it's going to be r. So it's going to be y over r. Same thing with x, or sine. So sine is going to be our, I'm sorry, cosine. Cosine is adjacent over hypotenuse. So our adjacent is equal to our x value, and then our hypotenuse is r. We're using r for like the radius of a different unit circuit or a different circle. So the tangent function is not defined when x equals 0. This occurs when theta is equal to negative pi over 2, 3 pi over 2, so on and so forth. So pi over 2, think about where pi over 2 is. This is pi. Pi divided by 2 is right here, or right there. That's what the equation was saying. So anytime you have a function that's right on there, or a point that's right on there, your tangent is not going to be defined. And so that kind of makes sense, because if you have opposite over adjacent, you're going to have this opposite number, which is going to be y, over your x, and your x is going to equal 0. You can't have 0 in the denominator unless you're Chuck Norris. And you all aren't Chuck Norris. So your tangent is not defined at that point. So watch out for that. So you're looking at domain and ranges right here. So the range for all of these functions, for sine and cosine is -1 to 1 for both of them. If you were to ever like plug these into your calculator, which you will someday, they look like this. But that's for another day. So given a point on a terminal side, you can use definitions to find the three corresponding, so find the values of sine, cosine, and tangent of theta. So I'm going to ignore kind of all this, and we're just going to kind of do it ourselves, and then we'll see where we get. So in this, I'm going to zoom in. In this triangle that they have drawn for us, because this point is -3, 4, we know that our x is going to be -3. Let me change colors. So our x is -3 and our y is 4. So with that alone, we're kind of good to go. Okay, I take that back. I was going to do with that theta right there, but that's fine. We can still do this. So we're working with this theta. So we need to know r, right? So we need to know what this r is. Now, can you think of any kind of theorem that helps us with a right triangle with an A and a B and a C? Pythagorean theorem, right? So we can say the square root of a squared plus b squared equals c. C is r in this case. So r is equal to 4 squared plus -3 squared, the negative goes away, square root of all that equals c. So 4 times 4 is 16 plus 9. So what is that? 27. Equals c. Or in this case, r, I should say. So let's see what they got. Oops. Can I not add? Yeah, I can't add. I knew that 27 didn't sound right. So then 5 equals our r rather than our c. So let's see, we're talking about that, Pythagorean. So anyway, what are we trying to do? We're trying to figure out our sine, cosine, and tangent. So if this r right here is 5, we know that this is 5 as well. So that's 5. This one right here is 5. And then we can connect these 2 points. Although we don't have a right triangle. Alright, let's see what they did. So we can substitute values of x and y and r into their definitions of the trigonometric functions. So we've got sine of theta equals y over r. So y is our 4, r is 5. So yeah, I was making this way too complicated. Cosine is x over r, -3 over 5. Tangent is y over x, -4 over 3. Too easy, right? So explain how you can determine the sign of the value of each function before substitution. So based on the quadrant that we're in, look at that, determine the quadrant and use the sign chart. So that's kind of, but I told you to be able to rationalize it yourself because that helps me. And you guessed it, we're going to have a real world problem. So use trigonometric functions to solve a real world problem. Out of all the things we learned, the trig is probably going to be your most likely to be used in a real world problem. In the real world, period. So an airplane on final approach descends at an angle of -3 degrees to the horizon, or to the horizontal, or the horizon, whatever. What is the change in elevation after it flies 6,000 feet horizontally towards the runway? When the plane is at an elevation of 3,200 feet on its final approach, what horizontal distance from the runway is it? So let me reread that. So sketch a graph with the plane. With the plane at the origin to find the change in elevation over 6,000 feet. So again, they made a picture for us. So this one is 6,000 feet. The horizontal distance traveled is the x-coordinate, and the change in elevation is the y-coordinate. So we've got the plane's initial position. Our x-coordinate is 6,000 feet. So that's this one right here. Yeah, that's what they gave us. And our theta here is -3 degrees. So what we can do is we've got our picture here. So we know this is 6,000. We want y. We let y. And we have an angle. Okay? So we need one of our trig functions that has the opposite and adjacent. And I'm sure if you haven't looked down there, that's going to be our tan, or our tangent. So what we can do is we can say our tangent is equal to y over x. So we plug tangent of -3, so we're right here, equals y over 6,000, and then we get to algebra, right? Come on, zoom in. So we multiply both sides by 6,000. That's where we come up to this part right here. And then this is where we can actually plug this into our calculator and figure this out. So where's my calculator? There you are. So you will notice that you've got all of your trig functions right here. Let's see if I remember how to. So double check to make sure that your angle is in degrees. Sometimes you may want to have them in radians, but right now we want them in degrees for this problem. Oh, go away. So then we've got, what was it? Tangent of -3 times 6,000. Uh-oh, that's not the same number. Probably means my calculator is in radians. So I'm going to have to look up how to change that, because that is a thing that we should all know how to do on our calculators. So I'll look into that. But when you plug this into your calculator, you're going to get y equals this number, and then you round it. And so that means that's our y value here. So that's the plane's elevation above, or the change in elevation as it's moving forward. So over 6,000 feet horizontal feet, the plane's elevation decreases by about 314 feet. The elevation change will be negative 3,200 feet when the plane reaches the runway. Use this fact and the angle of descent to find the horizontal distance. So in this case, we've got our plane, and we need to find our x, but we have our y, which is negative 3,200. And then we have our theta, I assume is still negative 3. So that is still negative 3 degrees. So again, we can still use tangent. So we're going to have tangent of theta equals opposite over adjacent. So negative 3,200 over x. So then you're going to multiply by x, divide by tangent of negative 3. So you're going to have x equals negative 3,200 over tangent of negative 3 degrees. And so you're going to plug that into your calculator and you're going to get this value. That means that in order to descend about 3,000 feet, the plane is about 61,000 feet away from the runway. So I told you that it's important to know how your calculator works, right? Well, I had to go look it up because I couldn't remember. But this is how most of your graphing calculators should work, to be able to change the trig functions to be either working in degrees or radians. So if you come up here to the mode button, so if you push the mode button, you've got the radian or degree. Whichever one is highlighted is the way that your calculator is in the mode of. So we're going to just use the arrow keys. We're going to push enter to make degree highlighted, and then you are good to go. So you can check that. So since we're in degrees, we know that like sine of 0 degrees would be 1, right? Or 0, that's what I meant. And then sine of 90 degrees would be 1. So you can kind of double check with some of your easier trig functions that way. So make sure you know how to use your calculator, because as you saw, you can't solve some of the questions unless your calculator is in the right mode. So there you go. That's our trig functions for section 15.2, and test them out on the Check on Learning.